So, welcome to our last meeting for 2023 uh, of the Astronomy Fundamentals Special Interest Group. Tonight, we have two topics, as usual, up for show and tell. One of them is on eyepieces, intended for those who are new to eyepieces and may not necessarily know what all the things they need to look for. And also, possibly for some stocking stuffer ideas or suggestions for you for your Christmas holidays, and that's going to be given by Stephen Ferris. And then our second topic will be given by Doug Smith, who will be discussing solar observing, I believe, techniques and equipment, or just techniques, Doug?
A little bit of both.
A little bit of both. Okay. You both should have presenter permissions. I'm not quite sure which one of you wants to go first.
Let Stephen go first.
Okay, Steve, if you don't
Okay.
mind.
This may take just a second because I've got to switch screens. But let me share screens. Hopefully this will come up because hopefully this will come up relatively smoothly because it's on a, there we go. Can everybody see this?
Yes.
Okay. In that case, I'm going to go to, where is it? View and slideshow, and hopefully this works. Okay. So to be completely honest, this is actually a recycled presentation that was originally given by Joe Jacoby on November 8, 2018. So it's about 5 years old. And it was given live. I was there for the original one. And because it was live and before we went on Zoom, it was not recorded. So part of the purpose of doing this tonight is to give us a chance to record this particular presentation. Now, just as a forward to that, Joe went into very exquisite detail on a lot of stuff that is very accurate, but stuff that may be a little bit confusing for new people who are not really familiar with some of the terms. So I'm going to maybe pass over a couple of the slides relatively quickly and stick with the stuff that may be a little bit more accessible. This is a fun one to do in December because eyepieces are a great gift for yourself or for whomever. I'm assuming you'd be buying for yourself. You wouldn't be buying for someone else. And so there's a lot of information here about what eyepieces are all about and what they do. In an age in which photography is becoming more and more popular and more accessible, it's nice to know there are still people who are doing visual observing. And eyepieces are a critical part of that. Typically, it was once suggested that you have as much invested in your eyepieces as you do in your telescopes. I don't know if it's necessary to do that anymore, but certainly there's a wide range of eyepiece choices, some of which are pretty affordable, some of which are extremely expensive out there. I won't be talking about most of the makes, but some of the designs, as you get more and more elements, of course, require more and more expense. There are some companies which are making these things relatively cheaply now, but originally they were multi-element eyepieces. All eyepieces are multi-element, but ones that would have 6, 7, 8 or more lenses in them could be fairly pricey. So just to go through this is, I don't know whose selection this is, if this is Joe's or if this is something he found on the internet, but it is quite impressive. I'm not sure you would need quite that many eyepieces to do typical astronomy observing, but it gives an idea of what this kind of looks like and what eyepieces look like. He's got a bunch of different designs and different focal lengths, and we'll go into what all that means in just a second. One thing I want to point out with this is some of the numbers that are included on the side of this, because the rest of the presentation goes into this without showing where to find those. Typically, eyepieces will show their focal length and a number of other features on the side, depending on what the make is and what company makes it. You can look at the eyepiece and figure out where these different details come from. I take a slightly different view on this than Joe did. So I'm going to emphasize maybe the stuff that I find important over some of the stuff that maybe was a little bit more emphasized in the previous presentation. So just to go on. unfortunately, I can't see some of this, but there's a bunch of different factors that go into looking for an eyepiece that works for you. Again, most viewers will have multiple eyepieces for different functions with different telescopes. I have about 10 or 12 of these lying around with different telescopes that I match with the telescope based on what my needs are for that particular telescope. I've collected quite a bit. If this was in person, I would be able to show some of those, but because we're online, we'll just go with the PowerPoint presentation. But one of the things you have to do is match the telescope image to your eye. And most of us are wearing glasses, uh, and it is a factor that our own vision quality does have something of an impact depending on what your particular eye needs are. Now, if you have perfect vision, you don't have quite as much to worry about, and we'll talk about some of the different issues that come in with eyes based on what you can do with eyepieces and not do with eyepieces. And of course, the technology improves. And so some of the things that maybe 10 years ago were much more difficult are now things that we can correct. But other reasons to have multiple eyepieces are to adjust magnification, increase angular resolution, and enhance the contrast. And we'll talk about ways to do that with different eyepieces as you go through your different choices. So some of the factors affecting astronomical image quality. Um, One of the big ones is atmospheric seeing. It is unfortunate that we don't always have perfect skies. In fact, even in Tucson, which has fairly good skies, we get plenty of nights of poor seeing, especially around times we have storms and things come through. Air turbulence causes that, and so it limits the resolution of the telescope and what you can do with it. So if you're looking for very high magnification of certain targets like planets, maybe the nights of poor atmospheric seeing are not the best times to jack up power. Also, the telescope performance. Different telescopes are capable of different things based on aperture and the quality of their own optics. So that can be a limiting factor. Eyepiece design is a limiting factor, and I'll talk a little bit about that in just a minute. And then your own eyes. It used to be that if you had near vision or were farsighted, you could use the focuser on the telescope to pretty much compensate for whatever you needed. And people like myself who had astigmatisms or cataracts or things like that were kind of out of luck. It's becoming more and more common now to have additional lenses that you can actually fit to the front of the eyepiece. If you have significant astigmatism, like certain companies will offer that based on your prescription. Now, it's expensive to do that. The other option, of course, is to use your own eyeglasses, but there are some complications with that we'll talk about in just a second. So atmospheric seeing is a big one. Clouds, winds, turbulence, and jet stream and dust. Something we have to deal with a lot in the Southwest is dust. Also in closer to the ground is ground convection, light pollution, and humidity. All of those can be factors in how well your telescope and your eyepiece can resolve images. This is an idea of atmospheric seeing. What you're seeing on the left is images. I don't know if this is through a specific kind of grading or if that's simply out of focus, but the point is that when you take the telescope out of focus and watch the image, if it's fairly stable, you can kind of guess that the atmospherics are fairly stable in the night. You'll get very clear images of things like planets and high magnifications. As the atmospheric seeing decreases, it gets harder and harder to see some of the details on the planets. And as you go to a higher power, of course, it becomes less and less likely that the eyepieces are going to pick out much. So seeing is a big factor in what eyepieces you may use from night to night. Probably not the biggest factor when you purchase an eyepiece. I apologize for the noise here, but I think I can do better right this second. So this is another example of atmospheric seeing. This is an issue that there's a number of different factors which produce different kinds of turbulence in different places, one of which is what's called orthographic turbulence, where on the side of the windward side of a mountain, you'll have somewhat more stable air than on the leeward side of the mountain, because the mountain, as the air goes over the mountain, can cause some turbulence as it goes over the other side. This is probably a factor in our part of the country, in places like CAC and even Timpa, when the wind is blowing strongly from directions that are coming over a mountaintop. Probably affects CAC a little bit more than us and Timpa, but point being is that mountains can do that. There's a lot of other factors, including the heating of the ground, and upper air turbulence, as well as jet streams and things like that come through. The point is, different sites that are fairly close by may have different seeing conditions depending on what is going on with the local wind conditions and atmospherics. And so you can't always anticipate what's going to happen in one site based on what's going on nearby in another. And I think that's the point that he was trying to make. This is a slightly messed up slide, so I'm not quite sure what that hodgepodge at the top is, but basically telescopes have certain features that limit their ability to resolve images as well. There's optical aberrations, which are inherent to every telescope design. There's optical manufacture quality, which is a huge issue with various kinds of telescopes. Generally, the price of the telescope, the more they've done to compensate for that. But even expensive telescopes have natural aberrations which go into their optical design, which optical designers have worked to compensate for. So again, price becomes a factor in that, but it also something that's inherent to the designs. And alignment and culmination are a big deal. What happens there is that if your telescope is properly aligned, properly culminated, you're going to have much better imaging than if you have a telescope that's out of culmination. Now, that said, I think a lot of people worry more about culmination than they need to with most telescope designs. They're pretty stable over time as long as you're not bumping the thing or you're taking over bumpy roads like on the way to Timpa. Although they have substantially improved some of those roads in the last year or so. But it is a factor that you need to check the culmination from time to time just to make sure that your telescope optics are still aligned properly. And then for the factors in the eyepiece, the critical things that we're going to be looking at in determining the quality are the design, the focal length of the eyepiece, the optical quality, and the optical coating. Now, the first three probably make sense. Optical coatings are very thin layers of certain types of materials that increase the transmissibility of the glass or produce other factors that may help with things like some of the color aberrations and things like that. Multi-coated optics tend to be a little bit more expensive than stuff that's not coated, but it does substantially improve the kind of image that you're going to get. So you'll see most of the eyepieces from reputable sources are going to use multi-coated optics. It might be good to ask some questions about what type if you're really into being very precise, but typically if it comes from a reasonable manufacturer, the coatings are fairly good. I have had eyepieces where the coatings sort of decayed over time, and that became a real issue. I won't name any particular manufacturers, but the coatings did kind of delaminate, and that became a problem as the eyepiece got older. But they're getting better with that, and the really good quality ones are typically going to last you for years or decades before they become a serious problem. And then the observer's eye, the astigmatism, which is where the big question I get a lot when I'm doing star party nights with the public, is whether or not to wear eyeglasses at the eyepiece. There are a couple different factors to that. But one of them is the eye relief of the eyepiece, which we'll go into briefly a little bit later on, but also your particular type of eye issue makes a difference. If you have an astigmatism, then it's probably a good idea to wear your glasses at the eyepiece unless the eyepiece is a very short eye relief. If you have a nearsighted or farsighted, you have the option of using the focuser and adjusting that, although most people have multiple types of eye issues going on at the same time, so it's not always perfect. Typically, though, if you're comfortable wearing your glasses at the eyepiece is probably the best thing to do. I don't. I personally prefer to take my glasses off, but then I simply have found it easier to use the eyepieces without them, even though I may not get the most perfect imaging out of that. Resolution of the eye changes as we get older. So we tend to lose a little bit of resolution as we age. Dark adaptation is a huge factor, and that is also impacted by age and a number of other conditions that I won't go into. Pupil size is also affected by age. Our pupils tend to get a little bit smaller as we age, which makes our ability to see things in the dark a little bit less. And then rods and cones. Rods are basically, if I remember my anatomy correctly, rods are there to see um, uh, things in black and white. Cones are primarily there for imaging. Cones also have higher resolution and are focused at the back of the eye, directly behind the lens in a spot called the fovea, which is where most of our high resolution daytime imaging comes. Now, the rods don't pick up as much color, but they are more light sensitive. And so this is where the averted imagination or averted vision comes into being a factor. If you can sort of look just off to the side of the target, especially if you're in low light situations, you can make out a little bit more than if you look directly at it. And that is true regardless of the eyepiece type. But again, as we age, our vision changes and some of the sensitivity goes away as well. So this is kind of a factor of why the pupil diameter determines the amount of light entering the eye. As when we become dark adapted, our pupils tend to expand and open up. And also we become more light sensitive overall. Age and dark adaptation significantly impact the eye performance at night, as does things like drugs and alcohol. So it's probably not a good idea to be doing a lot of drinking right before you go out and observe. Some people can do it okay, but some things like that can have an impact. So different eyepiece types, again, the original image, there's a lot of different types and functions. You'll notice that most of those are eyepieces. You have a couple of Barlow lenses and a couple eyepieces with what's called illuminated reticle, which is the little thing off to the side. It basically shoots a red light or a little red laser into the lens and causes a crosshairs or rings to illuminate. It's very good if you're trying to align a telescope on a star. Also very useful in finder scopes sometimes, but not something you use typically for most observations. And one of the things that was sort of a disadvantage of this thing is we talk about a lot of the designs, but not things like zoom eyepieces, which used to be a taboo topic in astronomy because they typically did not work very well. They were issues with the resolution and getting them to work properly was a little bit more difficult. They are improving, but they're not something I would highly recommend unless you are willing to be slightly disappointed with the image quality compared to just having multiple eyepieces at the same time. Barlows are another option, but they too have their drawbacks. So they're not always as a deal is just getting multiple eyepieces. So this is some of the designs that are out there. Notice, first of all, the number of lenses in the eyepiece. That becomes one of the factors that comes into it. Some of these, like the Kellner and the Koenig, were once pretty common in very low-end telescopes. Some of the ones that you buy off the shelf at a supermarket or at Christmas time or a store like Hobby Lobby has some of these, might still have Kellner eyepieces. I don't recommend them, and they're typically the most telescopes now are not equipped with them. They were at one point common, but they have all sorts of little problems with them. You can see that one of the problems is they don't have a lot of lenses in them, and that detracts from the kind of image quality that you get. Kellner's in particular, I worked with as a kid when I had a little Tasco, and the aperture of the lens of a high power lens, low short focal length lens is so small that you can't really work with it. It's basically a pinhole. And so they are not in any way highly regarded. Typically, what you'll find out there for sort of mid-range eyepieces that are fairly good, but do have some problems are the pulsals. One of the things to keep in mind with that is they too tend to have pretty small little aperture lenses for the short focal length eyepieces. But if you're using long focal length eyepieces, they can be a budget item that work fairly well. Orthoscopic, Naglers, and Erfels are much better quality. They have more lenses built in. Of course, you're paying for all that glass and for the craftsmanship and all that glass, because of course, if it's a well-built eyepiece, every surface has to be very precisely shaped. So you are not only paying for the high quality glass in there, but for the manufacture of that. However, if you can afford these things, they are definitely worth it because they will substantially improve your imaging, especially if you have short focal length eyepieces, because they have a much wider pupil, they have a much wider aperture, and most importantly, they have much better optical qualities in those kinds of focal lengths. So that would be something to think about if you're thinking about buying some eyepieces, is be sure to look at the type. Orthoscopic is good. Erfel and Naglers are the best. Naglers are, of course, were originally made by Televue. I don't know if that has ever come off patent, but they are the top of the line kinds of eyepieces. The design is fairly new. It only was come up with in the last 20 years. And there's some other even more exotic designs which have come out in the last 10, 15 years as well.
One other thing I would like to add on this before we transition away is that if you are shopping at like major telescope manufacturers, like say Celestron's website or Televue's website or Explore Scientific's website, they will each have their own custom brands of eyepieces. So don't take this list here as the definitive list of eyepiece types. Oftentimes those manufacturers won't even tell you lens configuration, which is handy with this diagram. They'll just say this has X number of elements in it.
Yeah.
So if you do find those, it's recommended, check out any reviews that might be associated with them and what people might be doing with them if you're interested in that particular piece.
And as a general rule, the more elements, the better. Not always, but that's sort of a general trend. There are other factors that we're going to go into that are publicly available, other than the actual optical design, that do have an impact, and we'll go into some of the details with that. Typically, if you're looking for a high power eyepiece, you want to avoid even fossils because of their very small little eye hole. But for some of the long focal length ones, they can be a very good eyepiece. So it depends on what you're comfortable with. They are much more affordable than some of the other designs. So I don't want to discount them. I actually have mostly Plossels in my collection. So I think they're a good eyepiece overall, but if you're looking for very short focal lengths, there is the exit pupil issue, and it can be a little bit less comfortable, especially if you are someone who's like wearing glasses and you have to move your head around to be able to see the image. But those are all things to just keep in mind. Then other things are the focal length of the eyepiece is measured in millimeters. It is important to keep track of that. That is one of the critical factors in an eyepiece. Focal lengths range anywhere from 3 millimeters to 55 millimeters. I rarely see 3 millimeter and I rarely see 55. The typical numbers are about 5 to about 40 millimeters. And counter logically, but it actually will make sense when I show the diagram in a second, the shorter the focal length, the higher the inherent magnification of the eyepiece. So typically, if you're looking at a 5 millimeter eyepiece, it will have a higher magnification than a 40 millimeter eyepiece. Now, that's not the only factor that matters, but it is one thing to keep in mind. Three popular barrel sizes. I'm not even going to go with 9.65. It is a system that was used by low-end providers, although some of the telescopes were good. The eyepieces were terrible back in the 80s and 90s. I rarely see these in existence anymore. You might get them secondhand. most common for reputable quality telescopes and eyepieces, though, is a 1.25 inch and the 2-inch barrels. And it does make a big difference. You need to know what your telescope accepts. Typically, if you buy the telescope with the eyepiece, it'll fit the barrel that the telescope comes with. But if you're buying eyepieces separately, make sure that you are matching the barrel size with the eyepiece with what's available on the telescope. A lot of telescopes today, especially if they're larger apertures, will have a set barrel size of 2, but they have an adapter that can go down to 1.25. My 8-inch telescope from Orion does that. And so just when you buy the telescope, make sure that if it is a 2-inch, that you can get an adapter to go to the 1.25 if you are using 1.25. Eyepieces, that is something that's kind of critical if you want those smaller eyepieces. They all work. It doesn't, the size does matter when it comes to the kinds of eyepieces you can choose, but it is something to keep in mind in terms of the adaptability of one to the other. Typically, if it is much harder to go from a 1.25 to a 2 than it is to go to a 2 to a 1.25. You just want to make sure you understand what your telescope has before you accept that. If you see 9.6 or not 0.965, it's probably best to get another telescope. Those are not your ideal instruments. They also vary significantly in cost. A 13 millimeter orthoscopic, back in the day, 2018 cost $50. A 13 millimeter ethos cost $575. I would imagine those prices are quite a bit higher now.
No, they're not.
For both. Really? Okay.
The orthoscopics still run 40, 50, $60.
Yeah.
And the high-end Naglers still run in the multi-hundreds.
Okay.
I just bought a 40 millimeter Nagler from Salstrom, and it was $4.25.
Okay. Okay. So I guess the prices of that hasn't changed that much, which is good to know. I recently bought a 40 millimeter, and it was still very affordable. It was a Plossel, but it was about, I think, $50 or so. So yeah, that runs about right. I don't know about the 13 millimeter. I haven't purchased something that's short recently, but that's sort of where we're at in terms of prices. Just be aware that different elements and having multiple elements and more exotic designs generally brings the price up pretty substantially. So that's a factor as well. Other factors are focal length, which we talked a little bit about, magnification, which is directly related to focal length, the exit pupil, which this original presentation went into a lot of detail about exit pupils. It does matter for the magnification and also for various kinds of aberrations that come into imaging, but I'm not going to go quite as much depth as Joe did into that. Eye relief is an important factor for those of us who wear glasses. It also can be, so if the eye relief simply is how far away from the eyepiece your eyes need to be in order to see the image. For those of us who are wearing glasses, eye relief is pretty critical because you can't, the eyepiece has a very short eye relief, you can't wear glasses, or it's very difficult to wear glasses on them. If they have long eye relief, then it's a little bit more comfortable to do that, or even possible to do that. So just if you are eyeglasses user, use that. Also, if you're interacting with the public at all, I've noticed that short eye relief eyepieces tend to be a little bit more confusing for people who haven't used eyepieces before than ones that have a longer eye relief. Of course, with the kids that like to jump in and hit their heads with the eyepiece and the like, so it may not be as big a deal for them, but for adults, it is a big factor. Apparent field of view is one of the things you're going to spend some money on. Probably not as much as it was 20 years ago, but that is something that some of the more exotic designs are designed for. And then true field of view is related to a number of factors, one of which is your magnification and, of course, your focal length of the eyepiece, along with the optical design. So focal length is one of the critical things. It's usually written on the side of the eyepiece. The focal length of the eyepiece, along with the telescope focal length, determines the overall telescope magnification and field of view. The basic principle, and this is using a refractor with the two element objective, and then you have the eyepiece in the way, and then the exit pupil location where you have the eye relief where the image comes into focus and you can see the image and how far away your head has to be for that. Magnification is directly related to the focal length of the eyepiece. The telescope is the way to find the magnification of the eyepiece. It varies from telescope to scout telescope and from eyepiece to eyepiece. The absolute rule is the telescope focal length divided by the eyepiece focal length. That's why you have the issue of why longer focal length eyepieces have lower magnification is that the denominator, of course, is bigger, and that produces a smaller number. And there's also the telescope aperture is divided by the exit pupil, which is a more complicated way of saying the same thing, but it is important because, say again?
Nothing.
Okay. Anyway, increasing the magnification increases the resolution and the limiting magnitude. Doubling the magnification reduces the object brightness fourfold. So the eye is more sensitive to low contrast objects when they appear larger. So the rule there, that is one of the reasons why a lot of people recommend that you should jack the power up as high as is reasonable to get an image. I personally disagree with that. But if you look at a lot of the astronomy sort of general books out there, they'll tell you you want a higher power eyepiece if it can handle that. The problem with that, of course, is you get into things like seeing and viewing conditions and the limitations of the telescope, which sometimes, in my experience, it makes the lower power eyepieces, especially mid-power eyepieces, a little more comfortable to use than some of the wider ones. Now, where you have small objects with very fine details like planets, you want to jack up the power as much as the telescope will allow. Again, different conditions allow different experiences. If you have a bad seeing night, jacking up the power is not going to help that much. If it's a really good seeing night, then that's the time where you want to push the power as far as you can go for small objects. There are a lot of very high-end eyepieces now, some of which are very affordable, which have pretty wide field of views for high magnifications. Now, not like you have with a 40 millimeter, but they are better than they were when we were dealing with little Kellner eyepieces back in the 80s. The point being, there's a trade-off. One of which is the brightness of the object is less as you magnify it because you're basically spreading out the light. And so if you're dealing with faint objects that are fairly wide field, you might want to go with a lower power to begin with. There's another thing that doesn't talk about, which is when you're trying to find an object without a go-to system, it's always good to start with the lowest power that you have available because it typically provides the wider field of view that allows you to see find the object a little bit more easily. Now, if you are with a go-to system or have higher power eyepieces with very wide fields of view, you can sometimes get around that. But when you do the basic observing like I do with a finder scope, there are reasons to just go with a lower power. Some basic facts: the most efficient magnification is determined by several factors, which is the size of the object, the brightness of the object or planet or nebula, and the resolution and contrast in current conditions. So again, what we talked about with seeing and visibility and things like that. This is, you have a lower and upper limit to how far you want to, what kind of eyepiece and what kind of magnification you want based on the exit pupil. Now, I haven't talked to that much about the exit pupil. It's basically the width of the band of light that comes out the eyepiece. So the lowest useful magnification typically has a 7 millimeter exit pupil. Beyond that, your eye can't your pupil can't stretch any further. And so you just get diminishing returns on how much light you can take in. In fact, beyond that, you really can't bring any more light into your eye. The highest usual magnification is a 1 millimeter exit pupil. That number, I would assume, is based on honestly, I don't know where that number comes from, but that was one of the things that Joe pointed out. If anybody knows why a 1 unit exit pupil is the highest usual magnification, I'm not quite sure myself. Doug, do you know that one?
Now,
Okay. The ideal magnification for a given object is the highest power to comfortably frame the object. So planets are going to be very different from things like the Orion Nebula, which is huge and won't fit entirely into the a short focal length eyepiece. This is a lot of math. I'm sure for you folks who are into that, this is a good chart. Basically the point here is that, the aperture of the telescope and the limiting magnitude are related, and I'm not going to go into that because I don't necessarily understand myself. And another chart that I'm just going to breeze by. If this makes sense, wonderful. It's a little bit of math for me. Again, seeing is a major factor is the basic thing that you're getting into. This makes a little more sense to me. And remember that the exit pupil, we're looking for a range between 7 millimeters and about 1 millimeter. So you'll notice that with a 35 millimeter eyepiece on a 10-inch f5 telescope, the aperture is 10 inches. The focal length is 50 or 1,270 millimeters. If you want to do the math, it simply gives you an idea of the length of the focal length of the telescope divided by the length of the eyepiece gives the magnification, which is 36, and the exit pupil, which is 7, which is our upper limit. You'll notice that with the 3 millimeter, we're exceeding that 1 millimeter limit. So for that particular telescope, you might have the eyepiece, but it may not show you any more than a blurry image. So there are limits based on what the eyepiece can produce. I typically there is a simpler way of looking at it, which is that typically you don't want more magnification than 50 times each inch of aperture, which is an easier way to put the same basic principle in the thing. I have jacked up my refractor a little bit higher than that, so there are some very good optics which might be squeezed a little bit more, but typically you don't want to do that, and that's under good conditions. Under bad conditions, you'll get less. Exit pupil is one of the ways of determining the magnification of the eyepiece. Again, it's basically that beam of light that comes out the back end is your exit pupil, and how wide it is basically the measure of the exit pupil. Is the diameter of the light cone exiting the eyepiece, and the exit pupil is a focal length, the eyepiece focal length divided by the telescope focal ratio. Or the telescope aperture divided by magnification. Now, Joe made a lot of slides in here about that basic principle. The basic idea is that a 1 millimeter exit pupil tends to be the highest power, and then 6 or 7 millimeters tends to be a lower power. One thing to take into account is that as you get older, your ability of your iris to expand gets a little bit less, and so those very wide exit pupils may not be of as much benefit as they are to folks who are a little bit younger. I don't want to go into a lot of detail with that.
Real
It
quick,
directly
Stephen.
determines.
So I think
Say again?
I was trying to remember back. So I think the primary reason that he had suggested 1 millimeter as the maximum has to do with the narrowest that your pupil can get. And so anything under 1 millimeter is going to be smaller than the narrowest your eye boob will ever get. So it's kind of more like it's a kind of a waste to get anything that has like an exit pupil of 1 millimeter.
Okay. He goes into a lot of detail about the millimeters of the exit pupil size. It is a factor to look into, but I don't want to go into the kind of detail that he did with that. Again, this is the same basic chart, just looking more at the exit pupil side. Again, that 3mm eyepiece may not be useful for this particular telescope. If you had a larger telescope with a longer focal length and like, it might be applicable. The point is, don't jack the power up beyond what the telescope is capable of handling under the specific conditions that it's under. He suggests that you space the exit pupils 2mm apart. For example, a 7mm, a 4mm, and a 1mm. Typically, I don't get into that kind of detail. I tend to do it by magnifications based on that particular telescope. So my own collection is very much based on each specific telescope. So, for example, with my little 80mm, I have only one eyepiece that I'm currently using. It is a 40mm, and the reason I use such a wide field of view is that I'm using it the eyepiece to find the objects or get the telescope into alignment before I put a camera on the back end of it. If you are looking for something that was a much higher power, just remember the general rule of thumb is 50 times magnification for each inch of aperture. So if you have a 2-inch telescope, you don't want to jack the power beyond 100 times. Now, there aren't a lot of 2-inch telescopes out there that are worth buying for visual use. Typically, they start about 3 inches or about 80mm. And in that case, you don't want to go much beyond 150. Now, I've done up to 200 on mine and come up with some fairly good images, but you need to know your telescope fairly well. A 2-inch times Barlow will double the magnification. It'll also double the effective focal length of the telescope. So if you're looking to do imaging through that thing, it can work for planets, but you probably don't want to do that with most of the wide field imagers that we have today. It also, Barlow's introduced a lot of aberrations of their own. So you want to be very careful with that. For if you're looking through a narrow field of view on a planet, it's probably a good idea. If you're wanting to do imaging through it, I wouldn't suggest it unless you're working on a planet. And then eye relief, he only talks about for very briefly, and I'm just going to go in a little bit more detail with that, the separation between the islands and the exit pupil. It typically determines the viewing comfort, and you need longer eye length for eyeglass users, like I said before. Also, for newer users, having a little bit more eye relief tends to be a little bit more comfortable for folks who haven't used an eyepiece before than something we have to get up close. So if you're using the eyepiece for the public, might be consideration. I personally prefer a longer eye relief thing, even with my glasses off, just because I don't have to hold my head right up to the eyepiece. But you want to keep that number in mind as well with when you buy it. An apparent field of view is a trick that has been introduced into, well, any eyepiece has an apparent field of view, but this is something where the modern eyepieces really have come to excel. So the apparent eye view is basically, if you look in the lens, how wide the field appears to be, and probably the simplest way to see if you look around how much that field of view seems to be. It's not the actual field of view on the sky. It's just what you see when you seem to see when you look in the eyepiece. So, for example, if you have 100-degree eyepiece, you're not seeing 100 degrees of the sky. You're just seeing 100 degrees from one side to the other of your viewpoint. It's complicated unless you try this, but just realize that when a lot of lenses are now being sold by their apparent field of view. So you'll see these big advertisements, 120 degree field of view. That's really not what they're saying. They're saying that if you move your eye around, you can kind of see what looks like 120 degrees of field of view, but it's not. It's about 2 degrees on the sky. So just be careful with that. One of the reasons it matters is that typically the wider the apparent field of view, the more comfortable the telescope the viewing is. And also the kind of more spacewalk effect you get looking through the eyepiece. So your typical, Plossol, the good eyepiece will have maybe a 50 or 60 degree field of apparent field of view, whereas some of these larger units will have a much wider field of view. Typically, this is what the effect is. Again, the Orion Nebula is only, a couple of degrees across or a few degrees across, but within a 100-degree effect parent field of view, you'll get a much wider image spread across, whereas with the 50 view, you'll only see sort of that inner part. They range from about 40 degrees with the smallest, simplest eyepieces to about 120 degrees. Usually the wider the eyepiece effective apparent field of view, the more costly the eyepiece. So again, those numbers have actually gone down, I think, a little bit. If you get some of the ones from like Celestron, you can get a fairly wide field of view for, or apparent field of view for something that isn't 575. Also, the make makes a big difference. So Celestron and Meade are probably selling ones for quite a bit less than that. Whereas if you're buying from TeleVue, which is the top of the line eyepiece, it's going to cost more. And typically, the larger the apparent field of view will show more true field of view at the same focal length. And true field of view is how much of the sky you're actually seeing. The actual span of the sky is seen through the eyepiece. The true field of view is the eyepiece field stop diameter divided by the telescope focal length times 57.3. Obviously, very logical. It is a good formula, though, to keep in mind for how much of the sky you're actually seeing. This matters with big objects. So the Orion Nebula, the Andromeda Galaxy, for really small things like planetaries. Yeah, it's important, but maybe not as important with the big ones. So this shows a 2-degree field of view again. So you can see the Orion Nebula there is the same images that we saw before, but this time it's showing how much of the sky you're really seeing. So you're not seeing 100 degrees of the sky, you're seeing 2 degrees of the sky there. So it's very important to keep that in mind, that apparent field of view is not the actual field of view. The true field of view is only a few degrees.
Hey, Stephen,
Yeah,
there is another formula for true field of view,
yeah.
and that's the apparent field of view of the eyepiece divided by the magnification.
Okay. So the apparent field of view divided by the magnification. Okay.
So if you had a 100-degree apparent field of view eyepiece and you were using it at a magnification of 100, you'd have a 1-degree actual field of view.
Yeah. And of course, the way to find the magnification is divide the focal length of the telescope by the focal length of the eyepiece.
Right.
All right. So just in summary,
it's a little easier formula to use because you don't need to know the field stop and all that.
Yeah.
You need to know the focal lengths.
Yeah. Cool. All right. So just in summary, he suggested you create a spreadsheet for all this. I'm not that technically interested in that. I'm more just matching eyepieces to telescopes. So what feels comfortable, the exit pupil is you want to match to the object brightness. The magnification is how big you're framing the object. And the sky conditions, the eye relief, longer is usually better. And that's been my experience as well. Apparent field of view versus true field of view. The reason I have emphasized that so much tonight is that a lot of the marketing around these eyepieces only talks about the apparent field of view. They're not going to talk about the true field of view too much. And that is deeply affected by the magnification, which is, of course, determined by the telescope that you're using. So when they say 100-degree field of view, realize you're not seeing 100 degrees of the sky on that. You might be seeing 2 or 3 degrees if you have a fairly wide field telescope. Cost is a big factor. I have noticed that a lot of the manufacturers are putting out reasonably cost eyepieces with good effects. Sometimes the eye relief on those is not the best, as I discovered with one of my eyepieces. But other than that, they're perfectly good eyepieces. And if you know what you're doing, you're going to be fine. And good enough is good enough. Don't go overboard. Especially this time of the year, it's fun to think about, oh, I'm going to buy a $600 eyepiece. And for one thing, that much glass is probably going to be very heavy. We call them hand grenades, but also that it isn't always necessary. You can get good eyepieces for reasonable costs, even with whatever deflation or inflation has happened.
So one other last thing before we transition. The reason you'll never see when you're shopping for eyepieces the true field of view mentioned is, as we've discussed, it's very dependent on your telescope. So they
Yes.
won't mention it because they're not going to say, oh, we were going to list 37 models of telescope to say what the true field of view is. The
Yeah.
assumption is that you, the buyer, are making that decision.
Yeah.
I mean, the same eyepiece will give you two different magnifications and two different telescopes,
Yes.
and hence you get two different true field
Yes.
views. So
Yes.
yeah, you have
And
to know your telescope.
that's a big factor too. If you have multiple telescopes, you're going to end up with different conditions just based on the focal length of the telescope. So that's important to remember as well. I'm a big fan of multiple telescopes, so I have to kind of think about this every time I switch from one telescope to another. But typically, that's why you want to know your as Doug said, you want to know your telescopes very well before you go buy an eyepiece, because it makes a huge difference. So a couple different things. StarZona has some piece basics and tutorial calculator. HellView, which is probably one of the top of the line manufacturers, also has an eyepiece calculator, and then Mel Bartels has an eyepiece calculator. And when we post the PowerPoint for this, you can take it off of that. And I'm just going to take a couple minutes for questions because I know we want to move on to the next presentation. And this one took a little bit longer than I expected. It was a very long PowerPoint, unfortunately. But if there are any questions, I'll take them now.
I'll add a couple comments.
Yeah.
So not so much questions. The thing about don't go overboard, I always keep in mind, and I always tell all my students in my fundamentals class and stuff when we talk about eyepieces, a good eyepiece will not make up for a bad telescope, and the reverse is not true. If you have a really good telescope and a crappy eyepiece, so watch what you buy. If you've only got a $500, if you've got one of these little 2.5-inch department store refractors, don't spend a lot of money on eyepieces. If you've got yourself a really nice telescope that costs you several $1,000s, like a big 10-inch Schmidt Cassegrain or something, then spend more on eyepieces.
Yeah.
The other comment I would make is you didn't parfocal. Keep that in mind. That's where all the eyepieces focus at the same point, and you don't have to refocus each individual eyepiece when you switch eyepieces. I find that that's a real useful feature too, is to have a set of parfocal eyepieces. And most of the major manufacturers offer those.
Is that something that's based off of the
Bernie here? One of the things I like to point out to especially Dob owners is watch out for the weight.
Oh yeah,
because the big heavy eyepieces that are available now, which in the catalog look wonderful and you pay a lot of money for, then you get them and you find out your Dob just goes right to the ground with them.
Yeah.
yes, I found that out.
I made that mistake with an eyepiece once where I wasn't aware, or I did not check the details that it actually was a 2-inch barrel and it's about yay big. And I thought it was about yay big. And of course, I was matching it to my Dob, which if it's pointed straight up, it'll work. If it's pointed anywhere close to the horizon, the telescope basically goes blank. And so it's the kind of thing where if you are going to do that, you want to get a counterweight on the back end or just get a smaller eyepiece. But yes, that is a very big factor for any scope, but especially for the Dobs.
Going back to your comment, Doug, on parafocal eyepieces, is that something that the manufacturers will take like an eyepiece set and that whole eyepiece set from that manufacturer will be parafocal with itself?
Manufacturers, they'll sell a set of eyepieces and they will tell you they're parfocal or they're not parfocal. And usually if the manufacturer is selling a whole set, they're probably parfocal.
Right. So if for those of you
and like I said, that is a really handy thing you can swap the eyepiece out and not have to refocus.
So for those of us that would have mix mash from different manufacturers, it's probably not something you're going to be able to distinguish by looking at a spec sheet. You would probably just have to take out the eyepiece and try it and see if like, hey, I have to refocus this.
You'd probably have to try them and see, yeah. Another thing that you could find, although it's really hard to find, and I've never heard of any manufacturer actually advertising this except for one. Brandon used to make superb eyepieces. They still do, I think. They're not out of business. Not only were their eyepieces parfocal, they all had the same eye relief, which was really nice.
And I don't hear any other questions or comments coming up, Stephen. So thank you.
We'll stop share.
And Doug, you do have co-host permissions, so you should be able to go ahead and share whenever.
I hope I got everything working so I don't get thrown out again.
So Doug has disconnected a couple of times during this meeting, so we're hoping his internet decides to, pull its magic out. So, but if he does drop, we'll pause for a bit because he seems to be reconnecting fairly quickly.
I've got my email up in the background so I can jump right back in again quickly. All right, come on now. Where's the... There we go. Okay.
I can see your slide deck now.
Okay.
Although you do have, okay, you're good. It still had a giant blank spot where something was shared over it.
Where's the, okay. Okay. Slideshow. Okay. All right. It's up. Okay. So my presentation is on observing the sun. So I'm going to talk about the different things you can do to observe the sun. Oh, great. My arrow keys aren't working. That's terrific. Okay. I got a comedy slide always. Okay. So why do we want to observe the sun? Well, it is, after all, the closest star. It's kind of rewarding to look at the sun. I always like looking at the sun. It's a bit challenging for most amateur astronomers because, for one thing, you have too much light. Usually we're used to looking at very dim sources where there's not much light, and we're always trying to enhance that. Here we have the opposite problem. We have too much. As a result, you need filters. We put all kinds of filters in for looking at the sun. The other thing that's really nice about looking at the sun is that it changes, and it changes quickly. It can change on the scorcher of minutes. The features that you're looking at can change considerably in just a couple of minutes. Another reason the sun is a nice target to look at is you don't have to worry about light pollution because you're in the daytime and you're looking at something that's really bright. Also, because you're looking at it in the daytime, you obviously don't need a red light and you don't need a star atlas. So a lot of easy things about looking at the sun. The Astronomical League has several observing programs for looking at the sun, at least 3, and there might be more than that. Let's take a quick look at what the sun actually is. So it's your closest star, and if we look at the interior of the sun, there is a core, which is about a quarter of the radius of the sun, is the core on the inside. And it's at a temperature of like 15.7 million degrees Kelvin. This is where the fusion is going on. The hydrogen fusing into helium is happening in the core. Then there is another layer which extends almost out to the outside, kind of about 2/3 to 3/4 of the way out from the core. It's called the radiative zone. And that's where the radiation is just moving through the stuff. And it takes a long time for a photon to get out. The material is very dense and very concentrated. It actually takes a photon approximately 150,000 years from the time it's generated in the core to the time it exits the radiative zone, because it's bouncing around. There's so much stuff that it just keeps bouncing around and finally gets out after about 150,000 years. The temperature ranges from 7 million degrees Kelvin at the inner boundary to about 2 million degrees Kelvin at the outer boundary of this radiative zone. And then the outer layer is what's called the convection zone, which the temperature is less than 2 million degrees Kelvin. And this is where you've actually, now the energy is being transported through convection, kind of like boiling water. And this is the outer shell of the sun, if you like. The gas cools, or it rises, and then sinks back down to be reheated, and then comes back up again. And during that process, energy is being released.
So real quick, for those of you who may not remember some high school chemistry facts, at the scales we're talking about here, Kelvin and Celsius are interchangeable. The difference between the two units is only about 273. So
correct. So, right. Yeah, all right. And the
Just-
actual surface of the sun, I didn't mention this, but the actual surface of the sun that you see through a telescope is called the photosphere. And that temperature is about 5780 Kelvin. And that's where you see your sunspots and your granulation and a lot of your other surface features. Okay, so that's a quick review of what the inside of the sun is like. And then the sun also has an atmosphere made up of a photosphere, which is the area closest to the surface. And that's where the light that you see, the visible light, is actually emitted. That's what you see when you look at it through a telescope. And that's where you see the sunspots and the granulation, is this little thin outer atmosphere called the photosphere. There's a chromosphere that's outside of that that glows very faintly, but the only time you're going to see that is during an eclipse. And then there's the corona, which is the very outer atmosphere, which is where the solar wind comes from. And the temperature of the corona is around 2 million Kelvin. And again, the only time you're going to see that is during an eclipse. Okay. Some warnings, always keep these in mind when you're thinking of doing solar observing. Never look at the sun with the unaided eye. You can damage your eye very quickly looking at the sun. Only use proper filters with your telescope or binoculars. Always check your equipment before looking at the sun. Check your filters to make sure there's no scratches or even pinhole type damage to them. Hold them up to the sky looking at the sun with your filter, and make sure that you don't see anything coming through, no sunlight coming through. And never leave a solar telescope out unattended, because someone else might come along and look and do something bad. And never, and I mean never use eyepiece filters for looking at the sun. Many years ago, when I was young, they used to sell these, what did they call them? Herschel wedges or something, that were basically eyepiece filters that you put on the eyepiece end of your telescope. No. Those things would blow up and crack and all kinds of things. You want to always use a full aperture filter over the front end of your scope. There's basically two types of full aperture filters. And the idea of the filters is you can observe the sun safely with a full aperture filter. There's the white light filter, which reduces the amount of light entering the telescope by 99.99%. And then there's hydrogen alpha filters, which are a different kind of filter, but they basically cut out all the light except for the light in the hydrogen alpha wavelength. The white light filters are what most people usually look at the sun with. They come in a couple varieties. They come in a glass variety. That's that one on the left from Thousand Oaks. That's a glass filter. And then the other ones are the film filters, which Connor's held a couple of workshops for how to build the film filters.
Yes, and
They
there's
work very
actually
nice. They
Well-
can be damaged easily, but they work nice. So that picture of the binoculars, he's got a couple of film filters stuck on his binoculars there, and they look homemade to me. But you can buy them if you don't want to make them. You can also buy them. They don't cost very much. They're inexpensive. The glass filters can get pretty pricey for large aperture telescopes. It can run into the hundreds of dollars for an 8-inch. The white light filters, that picture on the right, on the bottom right, by the way, that's my telescope with a 1,000 oak filter over the front, and my guide scope also has a 1,000 oak filter. I was taking pictures of a transit of Mercury across the sun's disk. So, the white light filters allow you to observe the surface features on the sun, sunspots, granulation, and some other surface features. And as I said, the white light filters come in two varieties. There's the film filters and the glass filters. The film filters you can buy from a number of different companies, or you can make them. Connor workshop again. And then glass filters, there's a couple of companies, but just about everyone I've ever talked to that has a glass filter has bought it from Thousand Oaks. So I think they're the main company for the glass filters. Hydrogen alpha filters allow you to view features in the solar atmosphere, not the features on the surface, sunspots, but now you can see the things that are happening in the atmosphere. You can see prominences and solar flares and coronal mass ejections and assortment of other things. That image in the upper right was taken through an H-alpha filter, and you could see that there's some prominences around the outside, and there's actually those dark lines that you see crossing the middle of the disk. Those are prominences, except now you're seeing them from above, not from the side. And so that's kind of cool. That picture on the left, on the upper left, is an actual H-alpha filter for a small telescope, if you like. Now, H-alpha filters get pricey really fast. You can get H-alpha filters and the blocking filter that goes with it for large telescopes, like an 8-inch telescope. You can, but it would probably cost you upwards of $5,000 to do so, maybe more than that. And they go up quickly the larger the telescope is. So some of a couple of companies they manufacture what's called a dedicated H-alpha telescope. That's all it can be used for, is solar viewing in the H-alpha. These telescopes are not very big. 2.5 inch. I've got a 2.5 inch, or smaller. I mean, Coronado makes these little 1-inch scopes. That picture in the bottom middle is one of the little Coronado 1-inch hydrogen alpha scopes. Coronado makes that one on the left. That's about, I think, a 2.5 inch or so. And then this one on the right is a Lunt. I think it's a 3-inch. Coronado is now owned by Meade, so you can buy them directly from the Meade website, the Coronado scopes. Lunt is a company here in town in Tucson, and that's where I bought mine. I got a Lunt and just drove over there and paid for it. These are still expensive. I paid a little over $2,000 for mine, but it's a whole lot cheaper than trying to buy a filter set for my 8-inch. And while it is only a 2.5 inch, and so you've only got the resolution of a 2.5 inch telescope, you have no shortage of light. You're looking at the sun, so you don't need to worry about not having enough light. That's not the problem. So you're sacrificing resolution in order to save money, basically. But these dedicated scopes now are becoming the in thing for looking at the sun in hydrogen alpha, because no one can afford to put the rig on their main scope. So what are the kind of things you can see? Well, in a white light filter, you're going to see stuff like this. You're going to see sunspots. These are areas of the sun that where the normal convection, if you want to call it that, has sort of been cut off by the magnetic field surrounding this area. And thus that part of the surface cools down. And so what you're actually looking at, it looks black. Sunspot does. It's actually still very hot, but it is about 1,500 degrees centigrade cooler than the rest of the sun. If you had this dark umbral area, the sunspot, out in the sky by itself, it would be almost, it would be very bright. Yeah, okay. It's the only reason it looks black is because it's cooler than the rest of the surface of the sun. And if you've ever looked at a picture of the sun's surface where you've got Venus or Mercury transiting across the surface, and then there might be sunspots on the surface at the same time, you can see the difference between where the shadow is of the planet, which looks absolutely black, and where the sunspots are. They don't look as dark. They're different. But this is something you can see, obviously, the sunspots. And you can see the sunspots with a white light filter or an H-alpha filter. They show up in either one. And they can get very large, as you see in that image on the right, in the upper right. It gives you a view of sunspots compared to Jupiter and Earth in terms of size. The sunspot groups can get really big. Sometimes they get big enough to you actually see with the naked eye.
Doug, you might want to point out that you'll never see a transit of Jupiter across the sun.
Yes, correct. You will never see a transit of Jupiter across the sun because Jupiter's orbit is outside of the Earth's orbit, so it never passes in front of the sun as viewed from the Earth. Another thing that's interesting to look for is when you're looking at the sunspots, the sun is not a solid planet. It's more like a gas giant in the sense that it's gaseous. And so it has what's called differential rotation. The equator does not rotate at the same speed as an area halfway up. Okay, if you look at this picture, you can see how the rotation speed is different for the two parts of the sun. The rotation period at the equator is approximately 25.6 days, whereas at the poles, it's like 33.5 days. So there's this differential rotation. And if you watch sunspot groups carefully at different latitudes, you'll see this differential rotation as the sunspots go across the front of the sun. And then the other feature that's nice to look at is the granulation. If you're looking at the sun with your telescope in the white light and you can actually see the granulation really well, then you've got a good telescope and you're looking under good seeing conditions, because sometimes it's hard to see. And this granulation feature, this is the convection, like the boiling water. This is where the hot gas is rising, cooling off, then going back down. And the dark areas between the granules is where the material is sinking, and it's cooler there, so it's darker. So it's bright in the middle, and then it spreads out to the sides and goes down along the dark areas around the granules, and that's where the material is cooler. Another feature that you can see in the white light is what's called the faculae. I hope I'm pronouncing that right. These are areas that are usually associated with the sunspots, but these are areas that are not quite sunspots yet, but will probably become active in the near future. So you're seeing like the pre-activity before the sunspots start emerging. And they can be seen in the white light. If you look at this image over here, you see these light bright areas here. This is what's called faculae. These are areas that are very likely going to turn into sunspots sometime in the near future. And then in the hydrogen alpha, you see them as these areas right here between the sunspots that are a slightly different color. Usually the faculae is best seen when it's near the edge of the sun, where the contrast is better, like right in here. But this is something you can look for with a white light filter or an H-alpha filter, like I said. Okay. And then the really cool thing to look at, if you've got IHL filter, is the prominences, okay, and what's called filaments. And filaments are actually the same as a prominence, except that the filament, you're looking at the prominence as viewed against the surface of the sun. The prominence is when you're looking at it on the edge. So in this image here, that's a prominence right over there. This big dark line here is a filament, but it's a prominence, just that you're viewing it from a different angle, so it has a different name. And there's actually quite a few prominences in this picture. There's one here and several along this edge here. And these are areas that plasma, this is cooler plasma that's being emitted off into off the surface of the sun out into space. And prominences, they can last a long time or they can be very short-lived. They might only be around for a couple hours, but some prominences have been known to be around for a year, some of the larger ones. Then, of course, solar flares. This is something that can be seen in H-alpha when it occurs. If it's a big enough solar flare, you could actually see it in a white light filter, although that's very rare. And it will look like that in H-alpha. You will see a sudden bright spot appear, and it'll be quite obvious. And if you see it on the side, it will be also quite obvious. It'll be quite striking. And they usually occur in the middle of a sunspot region where there's a lot of magnetic field activity going on. Coronal mass ejections, bigger and stronger than a solar flare. And typically you can only see them with H-alpha. As I said, one of the interesting things about viewing the sun is that it can change on the scale of minutes. So there's the top image is the granulation. This film clip is about 1 hour. Cut down, so it's really short, but you can see how the granulation is changing. It's bubbling, it's boiling. It's kind of cool to watch. And it's constantly changing like that all the time. And then the bottom one is showing you how a prominence viewed in H-alpha can change. Again, this is about a 1 hour clip, and you can see it changing dramatically in that short amount of time. This is probably the only thing I know of that you can look at with a telescope where the things change so quickly. There's the warnings again. I'll skip that. I put this at the end because I don't really like to push this, but I will say something about it. There is another way you can look at the sun. You can do what's called solar projection. And this is where you actually project the image of the sun onto usually a white screen like you see in both of these images. You can actually project the image off to the side if you have a Newtonian reflector, for example, or if you've got a refractor, you can set it up like this image here, where the sun image is being projected onto this screen down here, and you have this screen here. This thing here is just a shade to make shade around the image. I don't recommend doing this for any telescope. I lost my number there for the reflector. I had a 6 in there. I wouldn't recommend doing this with anything larger than a 6-inch reflector. And likewise, I wouldn't recommend doing this for anything over a 3-inch refractor. And you use the cheapest eyepiece, obviously, because you can damage the eyepiece by doing this, because you're concentrating all that sunlight through the eyepiece, and you can blow an eyepiece up really quick if something's wrong with the eyepiece. And make sure you cover your finder. The guy on the right with the refractor, he's got a cover on his finder, but I noticed that the guy on the left with the reflector, he did not put a cover on his finder. That's a little bit dangerous because some stupid person might actually look through the finder, and that would damage their eye. One thing about this, though, that I would say is good. If you were doing one, for example, the Astronomical League program, there's a program called Sun Spotters. It's a sun spotter where you draw an image of the sun like every day with the different sunspots and everything that you can see. Well, doing this, you can just put your piece of paper right there on the screen and project the image on that paper, and you can sit there with a pencil and draw the sunspots absolutely perfectly in the correct position and everything, and not try to do it, when you're looking through the eyepiece using a full aperture filter, you're kind of guessing where the sunspots are, you're approximating. So you can get really good, accurate sunspot diagrams this way. That's one thing. But I wouldn't do it if I have a large telescope. That's just too dangerous. Use a small scope. If you've got one of those department store refractors lying around, well, this would be perfect for that. Do the professional astronomers ever do solar projection? They absolutely do. I'm assuming some of you have been to Kitt Peak, or at least you've seen pictures of it. Well, here's the ultimate projection telescope, the McMath Pierce Solar Telescope on Kitt Peak. Its sole purpose in life was to project an image of the sun. The sunlight they're at the top of Kitt Peak, up here on the top, are a couple of mirrors that track the sun. They're about 6 feet in diameter, and they project the sunlight down this long tube, which is cooled, water cooled, and as a cooling apparatus to keep the tube from getting real hot. And that way, they want to keep the they want to keep the interior of the tube at a constant temperature so they don't have air currents and other disturbances in the tower. The light goes all the way down to the bottom, and there's a mirror down here at the bottom, then bounce back up to another mirror here, which is a cutoff mirror, which bounces the light down to this observation room where the observations are made. And basically, it's a giant projection telescope and projects this big image of the sun onto this flat white table you see right here in this picture. And that's how they would do their solar observations with that telescope. And if I remember right, though, they've shut this guy down. They're not using it anymore. But it's still up there. You can see it. So, okay, I'll take questions now.
Doug, you had mentioned at the beginning about the Herschel wedge. I believe that's Herschel wedges. They're still in use. We actually have one on one of our telescopes up in Minnesota. It's on a
Throw it
9-inch.
away.
We use it on a 9-inch refractor,
Throw it away.
and it gives a very good image.
Very dangerous, though, because you're concentrating all the sunlight on that.
But I think you were trying to refer to the old smoked glass. They were basically just pieces of smoked glass in a filter holder that you'd screw onto the back of your eyepiece.
Yes, those
And
two.
those were extremely dangerous.
So is the Herschel wedge. I would toss that guy.
Well,
Any type of solar filter that goes at the eyepiece and not full aperture, I think is very unsafe. Because you're concentrating all the heat from the telescope onto that piece of glass or whatever, your filter or your Herschel wedge. Seems to me that's just unsafe. I would recommend that you not use that anymore.
Could you go to that the page that's got the solar projection part?
Oh. This guy?
That guy.
Yeah.
So the telescope on I don't see a solar filter on.
These
on
telescopes,
the
you don't use a filter when you're doing projection.
Well, you're doing this. Okay.
Yeah, you're projecting out through the, this reflector on the left is just a standard Newtonian reflector. And so the light is just coming out from the eyepiece here. And that's why I say you want to use your cheapest eyepiece, because you could blow your eyepiece up doing this. Because you're pushing all the light through that piece of glass. That eyepiece will get hot. Okay. I've done this with a 4-inch reflector, and I didn't blow an eyepiece up, but you can when you touch that eyepiece, you can feel that eyepiece gets warm.
Do something else. Okay,
I see it. Yeah.
And then this is just a refractor doing the same thing, projecting the image down here. Okay, it's not a big refractor. This looks to be like a 2.5 or 3-inch refractor.
Okay, all right,
Doug?
thank you.
Doug,
Yeah.
do you have a double stack on your lens scope?
Oh yeah, I have the double stack.
You got everything.
Sometimes it looks better without the second stack, though. I don't always put that second one on.
Yeah. So what would you recommend for like when we have the eclipse?
Oh, for the eclipse. Oh.
I've
Well,
seen
that's
people
that's
do
coming
pictures
up.
with
That's
all
coming up.
three. I've seen people do photographs of the eclipse with all three, so they will all work just fine.
Yes.
If you're wanting to capture more solar activity during the partial phases of the eclipse, obviously the hydrogen alpha will capture more of that those details, especially because we're in a solar maximum period, so you might see more prominence details
coming up in the next year.
But they'll all work just fine. I've photographed the 2017 eclipse and the 2023 annular eclipse using a Seymour film filter, and you got on a 55mm lens. They work fine.
Yeah, I mean, a lot of people, what they do when they have star parties to watch an eclipse, which I assume a lot of people will be doing that this time around, they'll do this projection thing on a screen like this, because a lot of people can be looking at that at the same time. So you don't have a line of people trying to look through the eyepiece. You can have 20 people standing around looking at that screen, you know, looking at this screen here, watching the partial phases of the eclipse as it progresses across the disk. That's kind of a nice way to show an eclipse to a large group of people. And so a lot of times you'll see that at star parties or eclipse gatherings, that people will have projection scopes set up like this because it's easier to show a lot of people. But anyway, if you're, you know, for your own scope, if you're watching an eclipse, whatever works for you to look at the sun, white filter, hydrogen alpha filter, whatever works, you can do it and you can watch the eclipse. And when the totality part happens, you just don't look through the telescope anymore. You look up at the at the pretty picture in the sky.
So wrapping it up,
Any other questions?
I still only have, can you guys hear me? There's some weird things with my mic. So a little bit of last minute advertising. I am hosting another solar filter workshop on January 13th. I currently still have only one person registered, so there's plenty of room. If you are looking to make solar filters for some small to mid-size aperture binocular, telescope, or camera lenses, by all means.
Like these.
Yes, like those. Those look to be like a Beta film because they're a silvery texture.
Yeah.
But there is a lot more information in the club's monthly bulletin about the workshop, including some images showing what the two differences are between the filters. If you are interested, please check out that bulletin announcement for more information, and also contact the fundamentals at Tucson Astronomy for registering so that we can get you in. Like I said, there's still plenty of room. I only have one person signed up right now, so by all means.
Okay, that's it.
And with that, I'm gonna catch the recording there. Have a